Swayam Prabha. Digital India. Educated India.
Last class we started talking about Eutectioid transformation. This is different from precipitation in the sense here you get two phases out of a parent phase when compared to precipitation where you get one phase out of the parent phase. So, here we take a typical example of iron carbon system where you have the gamma which gives you alpha plus cementite, let us say, where gamma is the austenite, alpha is the ferrite and cementite is the Fe3C phase. And this is what we started looking at, and as you clearly see when you compare with the previous case of precipitation where you have an alpha which is a supersaturated solid solution is giving you alpha plus some phase, you can call it as a theta. So, here you have the parent phase remaining with a different composition of course, and a product phase comes out which precipitate out of the excess solute that is available in the parent phase. So, the parent phase is a supersaturated, and because it is supersaturated the excess solute comes out as this. So, here the parent phase does not vanish after the transformation, excepting that the volume fraction of the parent phase which is initially 100% would decrease to certain extent where the product phase takes over some part of the parent phase. So, that is why, so you would see that the parent phase remains, whereas in a Eutectioid transformation you would see in principle there is no parent phase left out, excepting in cases where you are talking about a hypoeutectioid or a hypereutectioid where there is a pro-eutectioid phase. In this particular case it could be a pro-eutectioid alpha or a pro-eutectioid cementite depending on whether we are talking of hypoeutectioid or a hypereutectioid. So, as a result you may have the parent pro-eutectioid phase, but not really the parent phase. If you take the parent phase as a gamma, gamma does not remain after the transformation, excepting again if the transformation is not complete. That is where you need to understand that if you go to the TT diagrams, for example, you look at a diagram like this where this temperature is what we call it as the A1 temperature. What is A1 temperature? 720. What happens at A1 temperature? Yeah, tell me. Transformation of what to what? Perlite to austenite. Okay. This is while heating or while cooling? While heating. So, we are now talking about the cooling. What happens while cooling? Austenite transforms to perlite. This is what we call it as the perlite. So, that is what you call it as A1 temperature. And in principle if you have a hypoeutectioid or a hypereutectioid, in principle you have another temperature which we call it as either A3 temperature in case of hypoeutectioid and what? ACM temperature in case of hypereutectioid. So, and that is obviously above the A1. So, you have another temperature which you can call it as A3 for example in a hypoeutectioid, and then if you can observe you would see another additional curve that comes in, and that is related to the formation of the what does form? Pro-eutectioid alpha from gamma. So, gamma gives you alpha in this domain. So, everything is gamma above that temperature A3, and between A3 and A1 you will have gamma plus alpha, provided the time that you are providing for the transformation is longer than what is decided by the TTT diagram. For example, if I am holding the alloy at this temperature, I have to cool the hold the alloy for a time longer than what is decided at that temperature, so that I can nucleate alpha. If I am holding for a shorter time, then alpha does not get nucleated, and that is why you say that anything to the left of this TTT diagram is basically what? What do you have to the left of the TTT diagram? It is metastable gamma. Do not call it as unstable gamma. Okay? There is a lot of difference between metastability and unstability, instability, whatever it is. So this is metastable. So this whole domain is metastable gamma. The reason I have to tell you the difference is unstable, it immediately transforms to something else. The moment I say metastable, for it to transform to something else, you need to provide an activation barrier. That is the difference between a metastable and unstable. For example, if you take a situation like this, I told you also an example possibly some time back. If you take a duster like this is in a metastable state. If I keep it like this is in a stable state. But from this metastable to come to the stable state, I need to push it. If I do not push it, it remains like that forever. So as long as an activation is provided, it does not come back to the stable state, and that activation is this. So it has a higher energy definitely when compared to the stable state, and in fact one can also show in case of the duster also, if it is something like this, if you draw the diagonals and represent the center as the CG, and that is at a higher state when compared to a state like this, where if you draw again this one, this is higher than that. If you represent this as the energy of this and this as the energy of that, this is higher than this energy. But when it is pushed, it goes through an intermediate stage which is something like this. Or possibly if I put it on the same base, and then finally goes to this. So here if I join these two, you come to a slightly higher level. So this, the CGs which is obtained by joining the two diagonals, is at a higher. So it goes like that and then comes like this. So it is at a higher energy state here when compared to this, and this is what we call it as unstable, because at that stage it does not need a push for it to fall. The question is which direction it falls, whether it falls this direction or that direction. It has a driving force to fall in both the directions. Only thing is, in the direction of the stable state it has a higher driving force, because this whole thing is the driving force for this, and whereas this is the driving force for this. Now depending on the direction of your push that is given, it will fall in a particular direction. So there is definitely a driving force for an unstable state, either to become a metastable state or to become a stable state, and that driving force to a large extent and the direction of the force that is available decides whether the unstable state becomes a metastable state or a stable state. And if you are starting from the metastable state and you have provided an activation energy, then it would go to a stable state. This is the example of Fe3C. We talk about it when you take Fe3C becoming alpha plus graphite. This is what we talk about. So you need to provide sufficient activation barrier for this Fe3C to split into the alpha plus graphite or gamma plus graphite. What does it depend on? Whether you get alpha plus graphite or gamma plus graphite? Temperature. Whether you are above A1 temperature or below A1 temperature is what decides whether you get alpha plus graphite or gamma plus graphite. And of course, for the alpha plus graphite and gamma plus graphite, the time required is going to be different. The activation barrier is going to be different. Why? Because this alpha plus graphite occurs at a lower temperature and gamma plus graphite occurs at a higher temperature. So the reaction rates are going to be higher for at a higher temperature when compared to lower temperature. So the time required for such a transformation, either alpha plus graphite or gamma plus graphite, can be worked out looking at what is the diffusivity that is available at a particular temperature, because it is the diffusion which controls the whole thing. So anyway, so this is all slightly beyond the thermodynamics, but one need to have always a knowledge of this kinetics, otherwise you are always having a half knowledge. So thermodynamics without a kinetics knowledge will not give you any information about the whole phase transformations, because the phase transformation is always a combination of the two. Okay, many times thermodynamics may say yes, this phase will form, but the phase may not form. But at the same time, one important thing that the thermodynamics tells us, that if it tells that a phase cannot form, okay, kinetics cannot make it form. Okay, so this is important. For example, if you are at a temperature let us say below the melting point, a solid will not become a liquid. Thermodynamically it is not feasible. So however fast reactions you do it, however you put a catalyst there, it will not be able to make a solid into a liquid until you raise the temperature. The raising the temperature can be by thermal means, by any other means. Okay, you can do irradiation, for example. Any energy can be converted to any other energy. So irradiation also can lead to such kind of a transformation of a solid into an amorphous structure, which you can call it as a liquid. It is almost equivalent to raising the temperature where the solid has become a liquid. So you need to provide energy for it to transform into the stable state. So thermodynamics definitely gives you clues what is possible, what is not possible. But at the same time, just because it says it is possible, it does not happen. That is why you take a liquid, bring it below the melting point, it does not mean that solid has to form. The liquid can remain as liquid. If that solid needs a large activation barrier for it to form, then the liquid does not form a solid at all, and that is the reason why in a number of cases we get glasses, because the liquid is not able to transform into a crystalline solid. And that is a standard example is our own silicate glasses, where you have brought the liquid below the melting point, but silicate crystals are not able to nucleate. So as a result, liquid remains as liquid until you reach the temperature of Tg, and where this liquid becomes a glass. So there are a number of numerous examples where just because there is a driving force, it does not mean that the transformation will take place. Okay. At the same time, you also should remember that driving force also helps us to understand kinetics to some extent. For example, we have been talking all these days that the delta G V controls to some extent delta G star. How does it control? Prerna, you know the relation? Yeah. Square, perfect. This is inversely proportional to delta GV square, but again that is only looking at the nucleation without considering any diffusion, Okay. So if you start considering the diffusion aspects, that is to a large extent controls the kinetics. There you would see that this activation barrier that we are talking, you need to add some other activation barrier to really know the nucleation kinetics or growth kinetics. That second activation barrier that we are talking about is an activation barrier for diffusion. If you add that, then you get a full picture, otherwise this is not giving the full picture. That is the reason why you will see that in a TTT diagram the curve is a C shape. The C shape basically means what? It tells you that as I decrease the temperature, what is happening? What does this time tell you at any given temperature? The time needed for nucleation. This is what we call it as the incubation period. All of you know that when any phase transformation has a typical S shape. If I plot fraction transformed as a function of time, this is something like 100%, let us say, and this is 0%. So, if I am talking of gamma to perlite transformation, it would have a typical curve like this, and this particular time where the transformation is starting is what we call it as nucleation, and this is what is completion. This is start, this is end, and this is what you will see in a typical S curve, and this period is what we call it as the incubation period. What happens during incubation? What happens during incubation?
Diffusion, the system tries to
Nucleate. That means what? An R star is something which evolves during that period. The atoms come together and form the size of the R star critical nucleus for decided by that particular temperature. Every temperature has a certain R star, because every temperature has certain delta G, and that delta G decides what is the R star, isn't it? You know that R star is again minus 2 gamma by delta GV, assuming a spherical nucleus. We have done this, possibly all of you must have done at the second year BTech level when you are talking about nucleation. So, this is something which you know. So, for a given temperature this is fixed, driving force is fixed for a given temperature given undercooling, and if that is fixed, this is fixed for a given nucleation, because once you decide what is the product coming out of which parent phase, then gamma gets fixed. Gamma depends on that. So, once gamma gets fixed, then R star gets fixed, and that R star, once for it to come out, you need certain time. Atoms have to come together, form that R star, and this time, if you look at it, if you carefully see here, the time is decreasing. Why is it decreasing?
R star coming down.
Yes, because R star is coming down. As I decrease the temperature, my undercooling is increasing. See, if I look at a temperature here, this is undercooling. If I look at temperature here, this is undercooling. If I look at temperature here, this is undercooling. Undercooling is always measured with respect to the equilibrium transformation temperature. For us, the equilibrium transformation temperature for this particular transformation is A1, gamma to perlite. So, with respect to the A1, if you measure, you would see the undercooling is increasing, and if the undercooling is increasing, you will see the delta GV is increasing, and then R star decreases. But this does not continue forever. That is where you would see the second part of the C curve, the lower half of the C curve comes into picture because of that. Though the R star is continuously decreasing, in principle, if I use that, you will see the R star continuously decreases like this. But though the R star is continuously decreasing, because of the diffusivities are decreasing as a function of temperature, D, you all know D is D naught into exponential minus q by RT. This is known to us. So, as a result, you can see as the T decreases, this quantity increases. This quantity is negative. So, the negative quantity inside the exponential increases, and once that increases, D will decrease. So, the D is decreasing. If the D is decreasing, the time taken for any particular size to form, any particular size of R star to form should keep on increasing, isn't it? If you consider a particular R star, let us call it as 10 nanometer size, whatever it is, because the diffusivity at some temperature T1 and another temperature T2, where T1 is greater than T2, because the diffusivity at T1 is higher than T2, the 10 nanometers can form in a shorter time. At T2, because the diffusivity is lower, the flux is slower, because ultimately the flux J is minus D dC by dx. The flux will be slower, and if the flux is slower, then the time taken is larger. So, if I put that, you will see another curve coming, that is the time taken for a given R star at any given temperature, and that you would see because of these two combinations, you would get a C curve. So, at temperatures which are lower, the time taken for the R star to form is so large because of the diffusion, and that is the reason why you would see finally a curve which is something like this. So, the combination gives you a curve which is of this nature, and this is only start of transformation, and you need to consider the end of transformation also, that means this part. So, for each temperature
As we decrease the temperature, won't the R star also decrease?
yes,
So in principle, I mean, even the time increases, the R star keeps decreasing.
R star keeps decreasing, but though the R star is decreasing, even for that R star to, however small it is, for it to form, you need atoms to come together, isn't it? For example, this is a case, this is a more difficult case because two different phases are nucleating. When I say R star of what? Okay, I need to actually talk about a lambda star in case of this kind of a thing, because a critical interlamellar distance forms, because it is a in fact, if you compare, for example, in the liquid to solid transformation, if this is a melting point, let us say, this is, let us say, is the C curve for the liquid to solid transformation. Even for liquid to solid also you will have a C curve. This critical cooling rate that we are talking about, for an alloy it would be maybe slower, because an alloy would be something like this. For a pure metal it would be something like this. For a bulk metallic glass it would be something like this, the C curve, something like a silicate glass. The C curve is shifted so much to the right that you need a very slow cooling rate for it to become a glass. So, it is that diffusion and the structure formation, basically it is the R star and the D combination will decide what is the critical cooling rate that you need to adopt. So, that is why though the R star is decreasing, for that R star to form you need time, and if the temperature is very low, the atoms move so slow that even that R star to form is very difficult. That R star could be even few nanometers, but even then for it to form, because the atomic movement is so sluggish. But in this particular case of this gamma to Fe3C, here when you talk of diffusion, diffusion of what? Here there are two elements that we are talking about, the iron and the carbon. Diffusion of iron and diffusion of carbon, both are important, and most of the cases in this particular transformation, actually what matters is diffusion of carbon, because carbon can move much more easily than iron. As a result, in fact, all the transformations, if you carefully observe, perlite formation and the bainite formation, it is all controlled by carbon diffusion. For example, upper bainite and lower bainite, when you talk about it, it is all carbon diffusion. For example, if you look at the upper bainite,
Sir, in this shape of C curve, if I have a metastable structure such that I have got more vacancies, and where the diffusion is controlled by vacancies,
correct, this will shift, obviously it will shift to the left,
and this will extend up to the lower temperature.
Up to the lower temperature until you come to another structure which can form, in this particular case let us say martensite. So, you can keep on undercooling the austenite until you come to a stage where you can have a martensite transformation, which is a shear transformation. That is what you will see, that if I keep on undercooling the austenite, let us say, carbon initially can diffuse faster at higher temperature, but iron cannot diffuse faster. So what happens is, at this particular case, when you are cooling gamma at certain temperature, you suddenly see this gamma, because the temperature you have come down is such an extent that the atomic diffusion is becoming difficult. For alpha to Fe3C, alpha plus Fe3C to nucleate is becoming very difficult, because alpha has entirely a different structure and gamma Fe3C has a different structure, compositions are different. So that means you need to have partitioning taking place. Carbon atoms have to go both into the Fe3C and get depleted in the alpha. So that means you need a long range diffusion to occur. So instead what happens is, there will be a short range diffusion and transformation takes place. What is that transformation? You will see gamma transforms to alpha. Yeah, there could be. So they can also shift the TTT diagram. We will come to it as after, once we understand iron carbon. Whenever you deal with it, you start with a simple diagram, okay, with a binary effect. Yeah, yeah, it is the whenever you are talking of a transformation of gamma to alpha plus Fe3C, let us say you have alloying elements, something like, let us say, vanadium or chromium or nickel. Now the question is, where do these elements go during this transformation? Before the transformation, they are all inside the gamma, including the carbon. They are all inside the gamma. It is this gamma which is now splitting into these two. If it is splitting into these two, depending on their affinity towards a particular structure, they will dissolve into it. For example, chromium, vanadium have a tendency to form carbides, let us say. They either dissolve into Fe3C and form a carbide such as FeCr3C or Fe vanadium 3C, or it can form its own carbides. Go means obviously at the grain boundaries of your austenite. They nucleate at the grain boundaries of austenite, the new carbides, till the whole transformation is over. And once carbon comes out of the gamma by the formation of a special carbides like vanadium carbide or let us say Cr23C6 kind of carbides, the carbon content of gamma has come down. Once the carbon content of gamma comes down, again this whole thing gets affected, the TTT diagram. How does it get affected? Tell me. What happens, let us say I have vanadium or chromium or any other carbide forming element and I am cooling this now. So the moment I am cooling it, because there is a greater affinity, yeah, it will shift to right. Sure? Yes, why? Because the diffusivity comes down. Why? Concentration of carbon decreases. So what? The question is, the moment the question is which forms first, that is important. If you think that there is a greater affinity for carbon to form a vanadium carbide or a chromium carbide rather than forming an iron carbide, these carbides are the things that will come out first from the gamma. The moment they come out first, they can act as a nucleating sites for the pearlite. As a result, you would actually see that it shifts to the left. And that is the reason why we always talk about, whenever you take an alloy, a steel which has a carbide formers, if you want to have a higher hardenability, you need to go to a temperature where they are all completely dissolved. If they are not completely dissolved, you will see that they act as a nucleating sites, and as a result the TTT curve shifts to the left. The time required for the nucleation is shorter because there is already a nucleating sites that is available. So these are the effects that you get when you have elements such as this available. If you have no carbide former now, no carbide former, that means something like a nickel present. Nickel does not form any carbides, then what should happen? That is where you see the diffusion plays a role. Because of the presence of nickel which is sitting in the substitution inside the gamma, this prevents the diffusion of both carbon atoms and iron atoms, because wherever nickel is sitting there is a strain, because nickel atom size is not same as iron atom size, it is sitting as a substitutional atom, and because of which the movement of both iron atoms and carbon atoms get restricted, and you will see the curve is shifted to the right. That is why we always say all dissolved elements in iron shift the TTT to the right. Whenever you have undissolved elements in the form of either elemental, for example cobalt is one such example, cobalt does not form any carbides, but at the same time cobalt also does not want to go into iron, it comes out, and that is what people have seen, that it forms because cobalt interestingly has a HCP structure, okay, which has some similarity with cubic structures, isn't it? At least one plane is there which has a similar thing, and more or less the packing factor also is similar. So there are certain similarities with HCP to cubic. So cubic structure, which is an alpha structure, can nucleate on that, and as a result the perlite formation becomes easier. Any one of the two, either alpha or cementite, if it can nucleate easily on something which is already available, then the whole perlite formation becomes easier, because perlite is combination of the two. The moment one comes, the second automatically comes out.
Sir, the carbide form may not be coherent with Fe3C.
True. So that is important. So in such a case what you see is that if for example vanadium carbide or titanium carbide is available, okay. So when vanadium carbide or titanium carbide is available, obviously around that carbide all the carbon content has come down. So it could even not only nucleate Fe3C, it could even nucleate ferrite, because all the carbon inside the gamma in a small region has been occupied by the vanadium. So it has taken all the carbon, so the gamma around the Fe3C gets depleted in carbon. That could lead to alpha precipitation just around the vanadium carbide or titanium carbide, and once that comes, then because of the thermodynamics, that at that temperature gamma alpha plus Fe3C is stable. So once alpha comes out, Fe3C comes out. It is not that the carbides are nucleating cementite, need not. But if the carbide has a structure which is similar to that of cementite, cementite may nucleate. But more interestingly, most of the non-cementite type of carbides in iron carbon diagram, they are all cubic. Vanadium carbide, tungsten carbide, you take niobium carbide, all of them are all mostly cubic in nature. So they would have an effect the other way. But ultimately one thing is true, that the precipitation, the formation of perlite becomes faster. That is what we are talking about, and this is what is going to lead to a second part of the diagram, and which is where you will see that you see the curve like this. Now let us look at this particular transformation which we started talking about. Let us say I am cooling it fast and brought it to a temperature which is below this, somewhere here. At that temperature the diffusion of iron and carbon both are becoming slower. So this kind of a splitting, and again I will answer Anisha that we are talking about alloy which does not contain any other alloying elements. Let us say in such a case, even if it contains alloying elements, if they are in the dissolved form, there is no problem. So in such an alloy, when I come to dissolved, means in the solid solution, it could be either substitutional, it could be interstitial, depending on which element you are talking about. If it is nitrogen present, okay, it is present in the place where carbon is also present, that means either octahedral voids or tetrahedral voids. If it is nickel, let us say, it is sitting in the iron positions.
Sir, I am taking still more higher size of this iron.
Then if the as you keep on adding elements with a higher and higher, what happens is only the solubility decreases, the maximum solubility. Good, the strain is more, and that is the reason why solubility is less. That is what we talked about when we talked about miscibility gap formation in a phase diagram.
Still how it possible, sir, for a single atom to replace that such a bigger and smaller atom?
it is not replacing. You people have to understand that there is always vacancies inside a structure.
But still, how it will go and sit in a smaller place, such a big atom?
If it cannot sit, it will precipitate with something else.
But we are
As
still talking of dissolving.
that is what I am saying. The dissolution takes place as long as it can dissolve. If it cannot dissolve, it will precipitate. As long as there is a let us say carbon available. Let us say iron and tungsten. Tungsten cannot dissolve into iron. What happens is iron and tungsten will come out. It is like iron and lead. Lead does not want to dissolve into iron. Lead precipitates out. And again, that is another problem. Such a precipitation is going to be, again, as far as pearlite formation is concerned, is going to aid in the pearlite formation, because you have a second phase sitting there. If the element cannot dissolve, it will precipitate out. There are so many immiscible systems. Iron copper is one such immiscible system. In fact, people are using copper as a strengthener nowadays. I do not know how many of you know about it. There are what are called IF steels now. What are these IF steels? Interstitial free steels, where the carbon content is 30 ppm, 30 to 40 ppm. Why do we want such a low carbon? Tell me. Formability, stretchability. You want the whole car to be made of one single sheet without welding a number of sheets. So, you want to basically stretch it to the whole body of the car, let us say, and it should have a high stretchability. Then the only way is to reduce carbon. But when you reduce carbon, strength goes down. So, how do I get the strength? That is where people are adding small amounts of copper. Copper precipitates as nano copper with a lot of twins inside, and such a nano copper gives a high strengthening. The reason again is because it is not soluble. So, not being soluble is also a blessing in disguise. We all know, for example, a very good example of lead. Lead is deliberately added to steels for many years. For what? For machinability. Free cutting steels we call them, isn't it? We know pretty well that it does not dissolve. So, the concept of immiscibility is used to our own advantage. Okay? So, in fact, people also use this for even in powder metallurgy components many times as what are called self lubrication. You add lead in leaded bronzes. Why lead is added? They are all bearing steel, bearing materials, bearing alloys. So, in bearing alloys you deliberately add lead because lead is soft. So, it acts as a lubricant when the bearing is there inside the component. So, the lead which is available on the surface acts as a lubricant. So, you know pretty well lead does not dissolve, still you add it because it does some purpose. Okay. In case of steels it is for machinability. In case of bearings we add it deliberately. Copper and lead do not dissolve into each other. So, you deliberately add lead to copper, understand. So, it is a question of whether it can dissolve or not dissolve. If it does not dissolve, we do not talk of dissolution at all. Whenever I say it dissolves, all these elements that we are talking, they all can dissolve, including tungsten. The only reason is tungsten can dissolve at a higher temperature. That is the reason why whenever we talk about high speed steels, the austenization temperature is almost 1200 degrees, 1100 degrees. Because tungsten carbide, for it to dissolve into gamma, you need very high temperature. The stronger the carbide, the higher the temperature you need for it to dissolve. It has to first break and then only dissolve, both carbon and tungsten. So, the higher, the stronger the carbide. That is why chromium carbide can dissolve at a much lower temperature. So, if you have a chromium inside the alloy, there is no problem, 900 degrees is good enough. But if you add vanadium, niobium, titanium, tungsten, the more you add molybdenum, all these elements, the moment you add, you need to go to a higher temperature. And now once you have them, now I am quenching it, let us say I am not providing sufficient time, I have brought it to a lower temperature here. At that temperature now I have to see what happens to this steel.
I have gone to the solution as well, sir. I finished it. Again I want to form niobium carbide. Since I got a strong affinity, it has to form at low temperature now, sir.
Correct. I do not need to go to high temperature, I am quenching it to a lower temperature, but at the temperature now if I want to see whether niobium carbide would form or not, definitely niobium carbide has a higher affinity. Higher affinity means larger driving force, larger driving force means smaller R star. So in principle it would like to form, so the R star for niobium carbide would be smaller than the R star for iron carbide, Fe3C let us say. Now the question is whether the diffusion rates at that particular temperature allow for that R star to come out or not. If it does not, then what happens is gamma gives you alpha of the same composition as that of gamma. Whatever is the alloy composition, let us say I am talking of iron carbon, the alloy with about 0.8% carbon let us say, and plus whatever elements that you are talking about. Okay. So if I take the alloy, we are talking about this alloy 0.8 carbon plus some alloying elements, all of them are in a dissolved state, and the whole alloy is quenched to a low temperatures, something below the second half into the second half of the C curve. Once I come there because the diffusion of carbon is also takes time, because the temperature is low enough, iron itself is difficult. Okay. So carbon also takes time. So what happens is this gamma, instead of giving you alpha plus Fe3C or alpha plus some other carbide, it would give you gamma gives you alpha. This is what kind of a transformation is this? It is a partitionless transformation, which is a polymorphous transformation, not an allotropic transition. I mean in one way it is allotropic transition, but there is no, we are not talking of a pure metal. So once this happens, now this alpha is containing a lot of carbon. What is the solubility of carbon in alpha? 0.025 at room temperature, at actually 0.025 at 723, 0.006 at room temperature, but I am having 0.8% of carbon. That means it is such a highly metastable state. This alpha which has formed where only a FCC structure changes to a BCC structure, which means it only needs a short range diffusion. So that short range diffusion has taken place, because short range diffusion does not need a very high activation barrier, it needs only a short activation barrier. So atoms can move by a shorter distance, and once this happens, so gamma of 0.5 gives you alpha of 0.8. So once gamma of 0.8 gives you alpha of 0.8, now you need to see that this alpha of 0.8 is not stable. It wants to somehow reject the carbon which is inside. Now the question of where does this carbon get rejected? That is where you see that this alpha, and because of only a structural change is taking place, if I have a gamma interface, the alpha that comes out will come out as an acicular form, because you are the nucleation is taking place at a lower temperature. So as a result, the alpha that is coming out will form on certain planes of gamma in order to get a coherency, so that you will see there is a habit plane between the gamma and the alpha. So you see that precipitation forms like a platelets rather than forming at a grain boundary as what is called grain boundary allotriomorphs. This is what people call it as Widman-Staten structure. Widman-Staten structures come at low temperature, because at low temperature, in order to have the strain compatibility or the interfacial energy compatibility, you would see that it would form on a specific planes, so that you can have a coherency. And once this forms, now the question is this particular alpha has a high carbon, it wants to precipitate out. Now that is where, depending on whether you are at this temperature or at this temperature, now the carbon, the diffusion has to occur not within the whole of gamma, but within this alpha only, and that region is smaller. So as a result, now if the temperature is high enough, the carbon can diffuse from the center of alpha to the edge of alpha and then form as precipitates along this interface of gamma alpha interface, and this is what we call it as upper binate, where the carbon can diffuse up to the interface between alpha and the gamma in the acicular structure of alpha and forms at the boundaries of acicular structure of alpha. And if the temperature is low, it precipitates inside alpha, and that is what we call it as a lower binate, because it does not have time for moving to this much distance. So, it is almost like our Al to Cu coming out, theta phase coming out of alpha. So, it cannot go and precipitate at the grain boundaries, it precipitates inside the grain. Similarly, here you will see it precipitates inside. And if you go to further lower temperature, where the carbon is not able to move at all, and as a result gamma does not transform to alpha by a short range diffusion, it transforms to alpha by a diffusionless process. That is where you get martensite. So, you see a clear cut difference between a perlite formation which involves a long range diffusion and an upper binate and lower binate. Both of them needs a short range diffusion, excepting that carbon diffusion becomes difficult for a longer distances. So, it either forms here or forms here, and if you go to below the MS, you see suddenly you will have a diffusionless transformation. This is similar to like a glass transition. I mean, if you want to compare with the liquid to solid. So, you quench it in such a way, come to below Tg, you get a glass. This liquid transforms to a glass. Similarly, this austenite, if I quench it below the MS, the only difference is it is a solid to solid transformation, whereas this is a liquid to solid transformation. Liquid to glass is a liquid to solid transformation, whereas gamma to austenite is a solid to solid transformation, and where there is a structural change involved. Remember, okay, gamma has a different structure and the martensite has a different structure, and this different structure is coming out because of a what is called a shear. We will talk about it when we talk about martensite. We will talk about martensite, whereas here there is no structural change involved. Okay, you have come to such a low temperatures where the liquid, none of the atoms inside the liquid are able to move, and as a result the liquid gets frozen. That is why we call it as configurationally frozen liquid, configurationally frozen supercooled liquid. So, this is the basic difference between this and this. So, there is a shear involved in that kind of a transformation. So, any solid to solid transformation has to occur either by diffusion or by shear. The moment you say that product phase has a different structure than that of the parent phase, otherwise the transformation is not possible. Whereas here you see that there is no atomic movement, the atoms simply get frozen the way liquid is, excepting the difference is that the viscosity is so high that you cannot call this as a liquid anymore. That is why we have to. So, this is mechanically a solid, structurally a liquid, a glass. So, that is the difference, whereas here the structurally itself this is different, martensite is different, excepting in cases where you do not get let us say BCT kind of structures. In fact, even if you do not get BCT structure, for example, there are so many iron based alloys where the martensite is BCC in nature. We will talk about it when we talk about martensite. Most of the cases what you see BCT comes only because of the carbon. If carbon is not there, martensite is in iron based martensite is always BCC. It does not mean that all martensites, there are so many martensites, nickel titanium you have a martensite, copper based alloys you have a martensite. In fact, shape memory effect, the whole shape memory effect is based on martensite formation. Okay. So, you have other martensites, but if you talk about iron based martensite, it can be either BCC martensite or BCT martensite. We will talk about it later.